Good morning, afternoon, evening, whatever time it is for you guys. Chapter 4 example problems. I'm going to skip 4.1 because it's pretty straightforward and go right to 4.2, which tells us 4.2. All right. It's tug of war. Yeah, absolutely. I can't find the problem. 1 second. 4.2. No, that's math box 4.2. Let's see. Here it is. 3-team tug of war. In a three-way game tug of war, team pull on ropes together at one central point. The magnitudes and directions of the forces exerted by two of the teams are shown in figure 4.4. Team 1 pulls in the negative y direction with a force of magnitude F1 equals 800 newtons. Team 2 pulls with a force of magnitude F2 equals 900 newtons at an angle of 35 from the y-axis. If the net force on the knot due to the three teams is 100 newtons in the positive y direction, what is the magnitude and direction of the force exerted by the third team? All right, let's do this. So we have a knot here. We got a force this way and a force this way. And F1 is 800 newtons. And this guy is 900 newtons. And they give us at this angle 35. I prefer to be consistent and work with this angle, which would be 55. All right. We need to get our F, X, and Y components. So we know that we have an overall force, which way? In the positive Y direction. So F net is going to be equal to 100 newtons, and then the angle is going to be 90 degrees. All right. So what we always do when you have forces like this, sum of the forces in the X, sum of the forces in the Y. Sum of the forces in the X equals 0, right? There's no, the net force is 0. So we've got this is going to be F1 X plus F2X equals F3X. Negative F3X, sorry. Negative F3X. So that's going to be 0 plus 900 newtons, that's positive. Cos 55 equals negative F3X. All right. Sum of the forces in the Y equals 100 newtons, 1,000 newtons, positive 1,000 newtons. All right, so F1Y plus F2Y plus F3Y equals 1,000 newtons. All right, and I want to solve for F3Y. So F3Y equals 1,000 newtons minus F1Y plus F2Y. All right. This guy is going to equal negative 516 newtons, by the way. F3X. Let's write that here. F3X equals negative 516 newtons. All right, now I hope you have all this down, and I'm going to get myself a little board space. Might as well, yeah, I'm going to get myself a little board space. So write all this down. I'm going to erase what we got here. All right, continuing on. All right. So we're on F3Y. F3Y equals 1,000 newtons minus negative 800 newtons. That was F1 plus 900 newtons sine 55. And so this is going to be equal to, if you do the math, 1063 newtons, F3Y. All right, so now we have the components of our third force. Now we have to just, we have the Cartesian coordinates. We need to convert them into polar. So that's pretty simple matter. So R equals the cosine of x squared plus y squared equals the cosine of negative 516 newtons quantity squared plus 1063 newtons quantity squared. And yeah, I'll leave that to your pleasure. I don't know what that is. And the angle theta equals tan inverse of y over x equals tan inverse. What is y? 1063 newtons over negative 516 newtons. And you solve that, and you have to note that that will be in the, well, let's see, fourth quadrant, right? Because y is negative, no, sorry, second quadrant. No, x is negative, y is positive. So that's going to be in the second quadrant. All right, and that's a nice problem. Chapter 4. Good stuff in that problem. All right, I'll pause and continue. All right, I want to go ahead and do a little extra deal about the block on the ramp, because this is everywhere in beginning physics. So you got a ramp and a block. And you got some angle theta here. All right, so we want to know its acceleration, which is going to be this whatever component it's going to accelerate in this direction. So whatever part of gravity that component is, we want to know what it is. So what we're going to do is we're going to, we know gravity, this is mg. And the normal is going to go up like that. And here we have the normal. I'm just sliding my vector down because I can do that. And this guy, I'll slide him down there. So this is some angle. And this is the part of mg that's going to slide me down, which is, let's say that's phi, mg sine phi. All right. And phi is going to be always the angle of incline, but let's go ahead and prove that. So we have this is our block, and here is our, I'm going to go ahead and put this guy here and this guy here. And that's just these two components. So this, if this is theta, that's theta. Now I'm going to put my normal here. It's normal to the angle of incline. So this angle is going to be 90 minus theta. All right, and now I'm going to put a norm 90 here, which is mg. So if this is, here we have 90, and if this is 90 minus theta, then this guy's going to be theta. So when you have a block on a ramp, the acceleration down that ramp, acceleration, F equals ma. Here, F equals mg sine theta. So F divided by m equals the acceleration, which down a ramp is going to be g sine theta. That is in the absence of friction. If you have friction, you've got to subtract it from that. But this is just to prove to you that the acceleration on a frictionless incline is always g sine theta. All right, moving on. 4.3, the fuzzy dice problem. Have to find it. So give me a little minute. All right. 4.3. All right, gorgeous. Let's see, here it is. 4.3, a pair of fuzzy dice hang from the rear view mirror of a sports car on a thread that has negligible mass. At what angle do the vertical dice hang when the car accelerates at a constant 6.6 meters per second? A equals 6.6 meters per second, A sub x, right? All right, in the x direction. All right, we have the tension, T sub x, or tension, which is T sine theta equals ma. And in the y direction, I'm not going to use that equal, I'll just use this. Y, we have T cos theta minus mg equals 0. It's not accelerating in this direction, right? It's going that way, but we have the tension, which is holding it down. All right, so I don't know what your book does. Your book does some kind of algebraic substitution, but what I'm going to do, I'm going to rewrite this here. I'm going to have T sine theta equals ma, and T cos theta equals mg. All right, and I'm going to divide one by the other, like that. And these t's are going to go, and these m's are going to go. And I'm going to get tan theta equals a over g. And tan inverse of a over g equals theta. And there you go. Yeah, this is this division is a great way to solve problems, and they do it a lot in the physics books. Divide one expression by the other. You can cancel out these values, and sine over cosine is going to be tangent. All right, that was 4.3. 4.4 says, one of the authors whose mass is 95.4 kilograms stands on a scale. What weight does the scale read? Well, weight is force. It's weight equals mg. So we've got a 95.4 kgs times 9.8 meters per second squared. We're assuming he's on Earth. That is 935 newtons. All right. Hoping to feel lighter and armed with the knowledge of Newton's laws, the author puts the scale on an elevator and takes a measurement while the elevator is accelerating downward at 1 meters per second. What weight will the scale read then? All right. Well, this is a bit counterintuitive, but the scale's reading the force on it. So the scale's reading the weight plus the acceleration. And I know that you're thinking that 9.8 going downward and the acceleration is going downward. So you should add it and it should be 10.8, but it's actually the opposite. You subtract it because what happens is when the elevator isn't moving, the man's pushing down on the scale's pushing back on the man. If the elevator is going upward, the man's pushing down on the scale, and since it's accelerating upward, it's pushing even harder back on the man. So when you go upward when you accelerate upwards in an elevator, you actually feel heavier. When you go downwards, there's less force, so you have to subtract that. So it's going to be 95.4 kilograms times 9.8 meters per second squared minus 1 meter per second squared. And that's going to be equal to 840 newtons. So yes, when you go down in an elevator, you feel lighter. When you go up, you feel heavier. And if you don't believe me, go ahead into an elevator and test it. Test it, because you'll feel that acceleration pressing you down on the elevator floor when you go upward. 4.5 is pretty straightforward. 4.5. Let's see, tension on a string, a horizontal force of 7.5 newtons is used to pull blocks connected by a string across a smooth horizontal surface as shown in figure 4.2.3. Block 1, M1 equals 0.5 kgs. And M2 equals 1 kg. All right, the mass of the string is so small that we can neglect it. What is the acceleration of the system? F equals ma. So we have 7.5 newtons divided by the m total, which is 1.5 kg. I don't know what that is. Did they solve it? You guys can wait. The value is 5 meters per second squared. All right, 5 meters per second squared. That's 4.5. 4.6 is the Atwood machine. All right. So what you got, the massless pulley. This is mass 2, and that's smaller than mass 1. All right. And we're asked to solve for the acceleration. All right, mass 1 is going down, so M1G, that's greater than the tension, minus T equals M1A. Mass 2 is going up, and so the tension is greater. T equals M2G, T minus, sorry, M2G equals M2A. All right, I'm going to solve for T. T, for this guy, equals M1G minus M1A equals M1. Oh, no, I'm not going to do that yet. Sorry. And the other guy, T equals M2A plus M2G. All right, so now I have two expressions for T. I'm going to set them equal to each other. M1G minus M1A equals M2A plus M2G. All right. M1G minus M2G equals M2A plus M1A. I just arranged it and got my G terms on one side and my A terms on one side. Did I do that right? Let's see. Let's see. Oops. Subtracted this one from both sides, added that one to both sides. Yeah, I did. All right. Okay. Copy all this down. I'm going to erase and move on. Okay, now let's see. Am I recording? I hope. Yeah, I'm recording. All right. All right. So we were at M1 I'm going to take the G's out. G M1 minus M2 equals, and I'm take the A's out, A M1 plus M2, and I'm solving for A equals G M1 minus M2 divided by M1 plus M2. All right, and that's that. Okay, and the next part 2 asks us let's see. Ask us which is tension greater than the weight, and well, obviously the weight when the block goes down, the weight is greater than the tension because it's accelerating downward, and when it goes up, the tension is greater than the weight. So that's pretty obvious. But then it does some nice mathematics, some interesting stuff to solve for tension. So let's go ahead and do that. All right, so we have 4.7. T equals T minus M2G equals M2A. All right, so that's the lighter one. So now we solve for T. T equals M2A plus G. All right, then I went ahead and got my expression for A from the prior one, which was A equals M1 minus M2 times G over M1 plus M2. And that was from 4.6. All right, so I'm going to take this expression for A and put it there. So I have now T equals M2 times M1 plus M2. This is A. Let's go ahead. Do this over M. Oh, this is minus, sorry. Minus. M1 plus M2 times G plus G. There. All right, so take that down. I'm erasing it. So I was at, yeah. So now I'm going to have T equals M2 G, I'm taking G out, times M1 minus M2 over M1 plus M2 plus 1. Wait a minute, I have to do, no. Yeah, I'm good like that. I'm good. All right. All right, now I'm going to get a common denominator. T equals M2G times M1 minus M2 plus M1 plus M2 over M1 plus M2. Got a common denominator. Now I'm going to take these guys out, this one and that one. So T equals M2G times 2M1 over M1 plus M2. So now we solve for T. All right. And this is weight of 2, right? So 2M1 over M1 plus M2. This is T equals weight 2 over M1 plus M1 over M1 plus M2. And let's see. Okay, so T is bigger because M1 is bigger. So this is bigger than 1. So T is bigger than the weight of 2. And we just know that because if it's going down or if it's going up, then T's got to be bigger because it's pulling that up. All right. That was 4.7. 4.8. 4.8. All right, we're going to use that block on a wrench, what we learned about that. Let's see. And these are all good, by the way, just to practice your mathematic gymnastics, if you will. You know, to practice how to solve equations. Really good stuff. A skier moves from rest at the top of a hill and reaches the bottom in 3.5 seconds. The hill makes a constant angle of 30 degrees to the horizontal, assuming that no forces resist her motion. How long is the hill? Well, there's no friction. So we have x final equals x initial plus v naught t plus 1/2 at squared. And if we call this 0, and this is going in the negative direction, that would be fine. Or we could call this the positive direction and have our force going in that direction. We keep them both positive. I think that would be easier to do. X final equals, we call this 0, 0. She started from rest, 0 plus 1/2 a, as we learned earlier, is g sine theta times t squared. So these terms go. So x final equals 1/2 9.8 meters per second squared times sine of 30 times, what was that, 3.5 seconds quantity squared. And your book is going to give this to at 3 times 10 to the third meters. That's 3,000 meters. Wow, that's fast. 3.5 seconds for 3,000 meters. Really fast. All right. And that was chapter 4. I think that's it. Let's see. That's it for chapter 4 example problems. I'll go ahead and post this.